Good evening. Today we are going to see one problem again, that is from question bank, and that is design of simply supported slabs. Now we have two types of slab, one that is simply supported and another we have that is corners. So now if we will go to IS, and then in this IS, if we will see table 26, we are going to use, that is for corners held down. So 26 table. So 26 table 26. Corners held down. Corners held down, or we have another name as restrained slabs. Restrained slabs. If we will see table 27, both are on page 91. Table 27. We are going to use, that is for simply supported slabs. Both are for two-way slabs. Simply supported slabs. And we have page 91. And both this table gives us coefficients for bending moment. Coefficients for bending moment. So now we will go with the problem of a simply supported slab. So now it is given, that is design a simply supported two-way slab panel having effective dimensions. Now again here, effective dimensions are given, so we need not require to add or subtract anything to find value of effective span. 4 meter by 3.5 meter, it carries floor finish 1.5 kilonewton per meter square and live load 3.5 kilonewton per meter square, M20 and FE415. So we have to solve this problem. Now we will go with, we have step 1. So step 1. We have effective span, and we know shorter dimension, effective span, shorter dimension is always the span. So we have therefore L effective, that is equal to 3.5 meters. Then step 2, we have trial depth. Step 2, we have trial depth. So we have trial depth. Now in this we have L effective upon D, and that is equal to basic L by D into modification factor. So we have basic L by D into modification factor. Now in this, as it is simply supported, so we have basic L by D ratio, that is 20. And therefore we have L effect D equal to L effective divided by basic L by D into modification factor. So basic L by D ratio into modification factor. And we have L effective 3500. Always we have shorter dimension as the span. So 3500 divided by 20 into 1.4. Now we have actually another clause, but that clause we have for 35 for simply supported, but as this is 3.5 kilonewton per meter square, and that clause we have, that is still 3 kilonewton per meter square. So that we cannot apply, which is 35 and 40. So from this we will get value of D, that is equal to 125 millimeters. So we have value of D 125 millimeter. Now we can go with overall depth. So we have D equal to D plus D dash. D dash is effective cover. So we have 125 plus 20. So it goes to 145. And therefore, provide overall depth capital D, that is equal to 150 millimeter, and small d we will get it as 130 millimeters. So this is second step. Now effective span we need not require to find, in problem itself effective span is given. So now we will go with step 3. So we have step 3. Step 3 we have load calculations. So we have load calculations. Now in these load calculations, we have first that is dead load and second we have live load. So we have a dead load. In this dead load, we have first that is self weight of slab. So self weight of slab and which we have 25 into D. 25 is unit weight of concrete and this is capital D. So 25 into 0.15 and we will get this value as 3.75 kilonewton per meter square. Then we have second that under dead load. So we have floor finish. Floor finish and value of floor finish. This is given as 1.5 kilonewton per meter square. So we have these as two dead loads. Now we have second that is live load. And this value of live load, this is given as 3.5 kilonewton per meter square. Now we have total load. So we have over here total load that is equal to. So we have this value 8.75 kilonewton per meter square. Now then we have factorial load equal to 1.5 into total load. Now we have total load 8.75. So we have 1.5 into 8.75 and we will get this value 13.125 kilonewton per meter square. Then we have WU that is equal to 13.125 kilonewton per meter. We are assume unit width of slab. Assume unit width of slab. Now next we have that is bending moment calculations. So we have step 4 bending moment calculations. Bending moment calculations. Now you can see this. If you will see table which is given above, and we have this table 27. So bending moment calculations for slabs spanning in two directions simply supported on all four sides. And therefore we have to go table 27 for this. Now we have formula. You can see this mx alpha x WLX square and alpha y my alpha y WLX square. So we will calculate value WULX square. Now WU we have calculated as 13.125 into LX we have 3.5 square. And from this we will get value as 160.78 kilonewton meter. Because this value kilonewton per meter, this is meter square. So this is kilonewton meter. Now we will calculate MUX equal to alpha x into WULX square. Now we have to find out value of alpha x and alpha y. So we have this as alpha x, alpha y. So this depends upon Ly by Lx. So we have Ly by Lx and that is equal to Ly we have 4 meter and Lx we have 3.5. And if we will calculate this value, then we are going to get this value that is Ly by Lx as 1.142 or something. So we can say approximately we have this value, sorry, 1.15. So it comes actually 1.1429 somewhat like this. So I will consider 1.15 and then 1.15. So it range between the two. So we have for alpha x. So Ly by Lx we have 1.1. Value is 0.074 and for 1.2 we have this value as 0.084. We have to find for 1.2 0.15 will be at center. If you will take average of this, you will get it as 0.079. And then we will substitute this value alpha x as 0.079 into 160.78, and we will get value of bending moment equal to 12.7 kilonewton meter. Now switch over to mu y value. Then we have mu y alpha y wu lx square. Now alpha y we will go. So alpha y for 1.1. Now we have that is second row. So we have 0.061 and 1.2 we have 0.059, and then we have for 1.15 this value becomes 0.060, average of the two, and then we will have this as 0.060 into 160.78, and we will get this value as 9.65 kilonewton meter. So this is fourth step, which is bending moment calculation. So table you have to keep in mind. Then we will go to step 5, which is check depth from bending moment consideration. Check depth from bending moment consideration. So from bending moment consideration. And then we will have this as mu for D, we have to find out Ru max, and we have formula for Ru max 0.36 FCK Ku max in bracket 1 minus 0.42 Ku max, and we have given Fy as 415, so we have this value 0.36 into 20 into 0.48 in bracket 1 minus 0.42 into 0.48, and this value comes 2.76 Newton per mm square. And then from this we can find D, which is equal to mu upon Ru max into B. And then if we will substitute these values, then we have mu we have calculated, maximum moment we have to consider. We have one value as 12.7, another 9.65. So we have to consider 12.7. So we will have 12.7 into 10 raised to 6 divided by 2.76 into 1000. And if we will calculate value of D, we will get value of D, and that is 67.83 millimeters. Now this value is less than D provided, and we have provided value of D, that is 130 millimeters. Then we have step 6. Step 6, and we have reinforcement. And now in this we have AST is equal to, if I will go generalize, 0.5 FCK upon Fy in bracket 1 minus root of 1 minus 4.6 mu upon FCK BD square B into D. Now if we will substitute all values, 0.5 into 20 upon 415 in bracket 1 minus root of 1 minus 4.6 mu, I will convert it into kilonewton Newton millimeter 10 raised to 6 upon FCK 20 B 1000, D is 130 square, and 1000 into 130. And now if you solve this, then I will get this value as 2891.57 in bracket 1 minus root of 1 minus, we have this value 0.0136 mu. And then we will put ASTX For this, we have to put value of mu, that is 12.7. So we have 2891.57 in bracket 1 minus root of 1 minus 0.0136 into mu we have 12.7, and that is equal to, we have this value 261.54 millimeters square. Check it, calculations you have to check. Then we have ASTY, that is equal to 2891.57 in bracket 1 minus root of 1 minus 0.0136, and we have MUY 9.65, and that will give us 196.42 millimeters square. Now we have AST minimum. We can take it as 1.2 into D, because we have 0.12%. So 0.12 upon 100 into 1000, which is B value, into D, it comes 1.2 D, and 1.2 into 150, and it comes 180 mm square. And both these values are greater than 180 mm square. So we have to provide this value. So greater than 180 mm square. And then we will go for spacing. So spacing for ASTX. So we have spacing for ASTX. So we have spacing equal to 1000. So we will use 8 mm diameter bar into, we have 50.28, and divided by, we have AST 261.54. And by calculations, we will get it as 1000 into 50.28 divided by 261.54, and it comes 192.24, which is less than both, that is 303D. And therefore ASTX along x direction, we have 8 mm torque at 190 mm center to center. And then we have ASTY. Now we have spacing equal to 1000 into 50.28, and we have another value 196.42 to 196.42, and we will get this value 1000 into 50.28, 196.42 is 255.98, 255.98 mm, and therefore we have to provide ASTY, so 8 mm torque at 250 mm center to center. So likewise, we have to go for this until reinforcement steps are sufficient. We need not require to go beyond these steps. So this is all about your simply supported slab, two-way slab. So we will stop here only. Thank you.